All right. So in this module, I want to divert a little bit and talk about what polycrystalline samples um, are like when we're doing diffraction studies in TEM. So again, I want to kind of open with a question. I think you have a lot of information from previous chapters, and so see if you can sketch what you think um, this single crystal pattern we've been looking at, right, in the single orientation that we talked about. See if you can determine what you think it would look like if it was if it was now turned into a polycrystalline sample. So see if you can sketch that. You know, it doesn't have to be perfect, but see if you can sketch in general what you think it would look like. And if you don't have a clue, just see if you can come up with an idea, and then we'll come back here after you do that and pause the video and come back. And we'll take a look at what you've got. All right, so hopefully you've had a chance to sketch what you think it'll look like as a polycrystalline sample. So let's look and see what I've got here. So this is similar to what we talked about in the when we first talked about reciprocal space and Ewald spheres. You'll remember that I did an example where basically we saw that instead of these discrete diffraction spots in reciprocal space, what we have is rings. And sometimes you might be able to notice actual spots on that ring, but in actuality, it just kind of looks like a ring, and that's because of the rotation now, right? The specific angle of the 200, or sorry, the 220 doesn't matter relative to the origin. The length does stay the same though, and so basically you create a circle around the central spot, and the same thing for 200. And so you end up with a set of rings because there are multiple orientations in that pattern. And so you can kind of think about that as a rotation, of the single crystal spot pattern. And so you get something that looks like this. So each one of these rings corresponds to a set of these. So the 220 set of HKL planes, which would obviously include all the negatives that we see here. Same thing with the 200, we would really have any of the 200 types like the negative or bar 200. And that's what we see in a polycrystalline sample. So again, that's from the fact that these polycrystalline materials have not only one orientation, but lots of orientations. And that's why you can think of them as basically a rotation around the central spot. But the radii will be the same. So each ring here that we see is that given R value. And you can still determine the R value for that set of HKL planes, just like we did in the previous example, only now we don't have those relative angles, right? There's that angle between planes no longer matters because of the skewing and the fact that there are multiple angles. And so you won't have those alpha values that we saw before. But we could do a similar calculation in terms of these values as well. Instead of rings, so if you have a lot of orientations, you tend to get a consistent ring. But as you get less and less orientation, so if you only have a few crystals, sometimes what you see is discrete spots still, and you won't see a consistent continuous ring. And so this just means that we have fewer crystals or particles, and therefore less orientations, and it becomes less continuous in these cases. And so you might notice those in some of the polycrystalline samples that you see, and that's what it is, because you are seeing certain orientations, but then there's gaps where you don't see anything. So that just means that there's less material, less crystals and less orientations than a more continuous one like you see here. Just a kind of a side note here, because you might have been wondering about kind of this thing that kind of appears in some of these. This is called a beam stop, and it's basically something that protects the cameras that we use, because if we let the transmitted or central spot go through, that is so bright that it tends to obscure everything else. It tends to basically white out the image. And so this is to protect the camera from that huge dose of electrons, and also reduce the brightness so that you can see all of these other spots. And so that's why, and some of them are done differently here. Some of the intensity is still let through, whereas this one it's basically completely blocked out. But that's what this thing is called. If you've been wondering, it's called a beam stop, and this is very common in these cases. And so, that's the transmitted electron beam, and if you let that through, you won't be able to see the rest of it, and you might even damage the camera being used. So that's just a kind of side note that we can mention here.